Before starting, I would like to ask you, so how many of you are undergrad students? No one? All of you are grad students? Okay. The title of today's talk is Bio-Microsystems, which is my research direction. I think, as an electrical engineer, I think we can contribute a lot to this, to resolve some of the biological issues. So that's my goal, and then I guess you could be very curious how an electrical engineer can move that direction. That's what I would explain today. And then particularly, I would like to have a little bit narrower theme of chip-scale architecture organs. As you can see this figure, this is what I am dreaming, and I am challenging the research. So organs, brain, kidney, liver, maybe we could mimic these systems in our chip scale. Chip scale, we have been, as an electrical engineer, we are so proud of this electronics revolution. Maybe we can do the same thing for this biological research. My general research field, as I mentioned, is assembling micro pieces between electrical domain as an electrical engineer towards the non-electrical domain. Non-electrical domain could be physical environments, pressure, air quality, water quality, or biological environment, right? A lot of diseases, a lot of fluidics, we want to study that. So between connecting the electronics and non-electronic world, it's not a simple challenge, it's really a big challenge. Some people might ask, why do you need to do so? My view is, not everyone agrees to it, but my view, at least, is we have such a powerful electronic system. We started from a small transistor, now we use electronics everywhere. We are the king of the common in today's IT environment. Maybe we can use these powerful tools for the study of other fields, then we might cause a more revolution. That's my view. So I named it as a pervasive electronics, and then making these puzzle fields together. That's my research. We all are, as an electrical engineer, very proud of this electronics revolution. 1958, first IC concept, Jack Kilby, right? What he did is how to control electrons and pore flows in this little surface. Then in 1986, we first developed the 1 million transistor microprocessor. That was 1986. And now we have a higher density of these electronics, and also we have a lot of applications. iPhones, right? Phones and computers. Wherever you go, electronics are everywhere, even in the car. So we are dreaming the same thing. If we can control the fluidics one by one in a single device, because the fluidics and the fluidic path are the most fundamental pathways all these biological systems work and they communicate, right? If we can do it, maybe we can follow this revolutionary path the electronics have gone through. If we can control these fluidics. If we can build a little bit more complex systems, complex functionalities, maybe in some days we can use these electronic complex systems for a lot of different applications. So the first micropump, which controls the small doses of these fluidics, was invented in 1988, about 30 years gap. As of 2002, only 500 microvalves to control these little things have been developed, demonstrated so far, compared to 1 million. But if you follow the timeline, maybe 2016 or so, we might be able to show this 1 million. And then in the future, maybe 30 years behind, 2040 or so, maybe we can do something as an electrical engineer to align to this biological community. So my research is how to connect the electronics on the left side of the device for the study of the biological system on the right side by studying these individual components and making them together as a functional groups, and then finally finding the applications in biological systems. Maybe first platform could be monitoring environments, right? Electronics and environment. Salt Lake City, we are living in one of the worst places in terms of air pollution, right? So maybe we could build chips that combine all these fluidics together so that we can control these individual biological and chemical molecules. Maybe we can build some of the chips. This is one of the platforms that I'm working on, but I'm not going to discuss today. And two of my students who are there are working on this project. But today, what I'm going to talk about is another platform that might be of more interest to you. So maybe pervasive electronics, you can use this one. You can probably contribute to the health science by reducing some of the animal sacrifices. So each year, about 20 million animals are used in research in the United States just to test drugs, right? And then for those of you who are working in the bioengineering, you also use monkeys, right? And puppy, and rats, and rabbits, as you can see. It's like, I don't know, you have seen this. As an electrical engineer, I have a full respect for bioengineering, but maybe there are something that we could contribute by if we can replace these animals, right? So that's kind of my goal, and that's why I named one of the narrow topic as now artificial organs on the chip. Maybe could we replace these animals with the chip? In other words, could we mimic these organs in animals in the chip? If we can do that, we have the powerful fabrication techniques. Maybe we can start some revolution. So this is one of the visions when I first came here. So if we can make a little chip, which combines this, mimics some of the organs, like a lungs, air is coming into the chip, heart pumps the liquid throughout the chips, and in that area, we can grow these cells, and we can mimic the liver cells, we can grow the stem cells, we can grow the tissues, we can grow fats, livers, kidneys. Maybe we can do something interesting to mimic these biosystems. We can contribute to the cancer research. So that's the 3 years my group has focused on to address some of the challenges to build this, to realize this dream. Still, it is an ongoing work, right? So we identified the 3 challenges. One is micro-scale and accurate fluid manipulation system, so basically microphones and micros. And second one is comprehensive parameter control for the for temperature control, fluid control, how to sense the components. And the third one is how to build these systems. I think my group has all these has the capability to resolve all of these issues. So first, let me go to start with a very boring topic, which is called micro gas pump. Micro gas pump to introduce eventually to build the vision to introduce the gas or the air molecules or air flows into the system, which is a very difficult question. The reason is gas is compressible. So if you are in the swimming pool, all of us lined up, and then we start doing this, and then eventually we can make the whole water circulate somehow, right, within the pool. But we are sitting in this room. Maybe we can line up around this room, and then we start doing this, right, in one direction. Can you generate the air circulation? No way. Because gas is compressible. So when you have the solid object, you push it, then it will be pushed. But air, whatever you do, because it can itself can be compressed and come back, right? It may not be pushed away. So that's but in the micro domain, it becomes more difficult. In this tiny little volume, how can you do that? So that's the first question we answered. So we started with this concept by looking at mechanical analogy. So that, this liquid fluid companies are pushing this object with a rigid rod. You can push it. But if you replace this part with a spring, it's really hard and complex. So we got the idea from this little spring. Spring is moving. So when it moves, it inflates its body, and let these airs all come in and then squeeze it, right? But if you look at it, I forgot the video. If you compare the big guy and small guy, there are differences. Big guy, it does do this very slowly. Little guy, right? They do very quickly, which means they are very much related to what we are familiar with. Electrical engineer, we are the king of this capacitor and inductor and resonance frequency, right? So whenever you have the space, and then you can have this repeated periodic compression, and you can do all these calculations. Maybe this structure, mechanical motion of this speed, could be similar. So we modeled it, and then we can say that there is a cavity, and then at the entrance, there is a little plug of the air, which can start vibrating, right? Which can vibrate as just like you have a Coke bottle, and then you blow it, and at some frequency it will start making noises, right? Sound. So we just made the modeling, and then we found out that this modeling, mechanical modeling, is very comparable to the electrical modeling. Resonant frequency can be calculated, and also thrust can be calculated. So the thrust means that we can generate some air flow. So based on this, we mimicked the system. We made the first little squid. It doesn't look like a squid at this moment, but we have all the components: cavity, body, and then there are some inlets that air is coming in and out, and then there is a membrane. This is the body, the flesh of the body. So it comes in when the membrane compresses, air goes out, right, out of this chamber. And then when it goes back to the original position, air comes in. But there are very important physics phenomena, which is called net zero volume displacement, which means that the amount of volume comes in and out are supposed to be same, right? Do you agree? But when it comes in, it comes from 4 different directions. But when it goes out, because of this guideline, it will go out in one direction. So the same amount of air comes in and out, but because of the directionality, when it goes out, it generates some jets, right? It starts creating momentum difference. So if we repeat it very fast, probably 70 kilohertz, 70,000 times per second, then maybe we can generate a lot of momentum. So we built this with the MEMS screw. We are very good at microfabrication. And this is the membrane, about 1 millimeter size. And then this membrane is vibrating this way. And then air is coming and out this around these slots. And then of course this is built-in chip scale. So of course the frequency is low, but just to show it. And then once you have this array, then you place your chip here, and then can you see these jets, right? So this is a little computer chip, nothing else, no behind the scenes, and then connected with power. And there are some, I made this artificial, this cloud or something. And then once you start, then you can jet. So this is pretty cool, right? Now we can use the computer chips to generate some air, control the airflow. Maybe we can use this for, in some days, we can make these chips fly, right? Why not? You know, we got a challenge, right? So we tested the thrust, and this is the chip hanging at the end of the thread. And as it generates this momentum, jet with the momentum, it starts, you know, doing the pendulum motion by itself. So this is proof of some of the work. And then, of course, to push in the micro domain, to push it through these little chips, you need a very high pressure. Not just the flow is not enough. You gotta generate high pressure. So how to do it? We just connected them in series, in short. Of course, PhD is not able to just as simple thought, right? A lot of modeling tells us there has to be a certain design criteria, which is called the compression ratio here. And then so we built a micro device just like this. So which means, so this micro device is the same as the previous one. The previous one has only one of these, right? But now we have one, then on top there are two, and there are another membrane which is called the micro valve. So it controls the flow. You know, sometimes you block it, and sometimes you open it, sometimes you block it and open it. So we made it so then these little gas molecules will pump through this guy, but because they are connected in series, the pressure will be accumulated very high. So I assume I skipped this one. Nobody will understand this. So, but the key point is that now control aspect. So air, you can generate flows, but can you control well? Indeed, yes. So whenever these membranes move up and down, there are certain timings you can open, close, right? If you open late, then the air will be compressed longer, which means the pressure generation will be larger, right? But instead, the transition time from one chamber to the next will be shorter because it's opening less. In that case, we can generate higher pressure and lower flow rate. If as soon as this membrane starts compressing the air bottom, as soon as immediately if you open the valve, then of course you're gonna give them minimum compression, so which means less pressure generation, but the maximum flow transition, therefore maximum flow rate. So if we can do the control, and then we can control this high flow rate and high pressure. So we did the fabrication. This is a wafer. Wafer is this thickness is 500 micrometer, 500 micrometer for 1 millimeter, and then you do all this beautiful work, and then build the electrode for electrical conduction, and then there is a membrane moving up and down. These are another membrane which has support so that you can control the flows. So this is a built one, US quarter coin size, about size and thickness. And then these are the final work that we showed. We showed about high flow rate for SSCM and then 18 kilopascal compared to other works well. The reason I'm skipping all these plots, you would never remember, but I will show you the video which you will agree with. Oh, maybe I forgot to connect. Sorry for this. So you have this little pump over there, and then it is pushing the air, and air comes in through this one, and then coming out of the water, which means this pressure is high enough to overcome this tension at the water, right? And also the height from the location of this end of this tube to the water surface, that height is imposing some pressure, right? So this pump is overcoming that much of the pressure plus water tension and generating flows. If you can kind of guess, approximate the size of this bubble and then count them per minute, then you can calculate the flow rates, how much it is. So that's one video. And then probably we can more clearly show this one, so that air pump flowing air into through the channels, and you can move the air. To visualize it with the liquid drum. But eventually what we are trying to say here is, we can control both gas, we can control the gas flows in the microchips. Now this is about the liquid control, but before that I would like to go back to the state of the art. This is the best, probably the most complex microchip in the world so far. This was published in Science 2002, developed by Stanford. They built this one. So they want to use this for micro-diagnostic chips, right? And they want to do the cancer research and so on. So whatever it is, what they did is that they used 256 micrograms here. And then they published the science. It has a very high, it received very information. But if you look at the outside, look at this one. These are all the pneumatic controllers. So what it is, okay, this is the basic reason why we cannot integrate 1 mega transistor, 1 mega microvalve. To control each valve, you need a fluidic line, which is connected to the gas cylinders, and then in outside you are doing this. If you have probably 250, probably 10, 12 amps, then maybe you can do this at the split back, right? And maybe it becomes impossible. So this is the maximum they have reached. They used about, according to them, 7 fluidic gas cylinders. And then they were able to control 256 microvolts, maybe 9, because 2 to the 9 is 2 to the 8 is 256, right? Plus 1 control line. So unless we remove this guy, we will never be able to control the liquids in a lot more complex system, and therefore we will never be able to build those organs on the chip. So that's another goal we are targeting. So then why these guys did use this one? It's a fluid controller and gas cylinders. They are studying in Stanford. They are not fools, right? But they still used this one. Someone like me, they knew. Someone like me would criticize this. What the heck is this? It's published in Science, but on the web, look at this one. Right? Of course, in Science, they didn't publish this much. So the reason is, in the micro-scale pumps, never reach to the point of the sufficient force and pressure. They can control all these flows in the tiny scale. They had to use this to the gas cylinders because gas cylinders, which are big, can pump up with very high pressure and force. So unless we can find a way in the micro domain that generates very high force and pressure so that we can replace these guys, we will never solve these problems. And this is currently one of the major bottlenecks in microfluidics. So how can we solve it? Any solutions? I will hire you as my best. So our suggestion is this hydroelectric. Look at this guy, right? This car, and then building up, I have lifting up very heavy stuff. My grandmother, she's very old, but she just literally pushes the car brake and then car stops, right? So there is a force amplification mechanism in macro scale. So we want to bring it to a micro domain. So we build a kind of micro brake or micro cranes so that we can increase the force and or we can increase the displacement compared to typical movements. So if we can amplify the force of displacement, then we should be able to control something. And electrical engineers' backgrounds always helps. So I built it like a memory chip. Memory, I don't know, you learn about it, you have learned about it. Memory is controlled by row demux and the column demux. Whenever there comes the two signals come together, you are going to open, right? Read or write on that particular memory spot. So I just built it the same way. So basically this is the structure. Assuming this is very narrow, this is very large, 100 to 1,000 to 1. Then maybe slight movement over here will amplify and generate 1,000 times, 100 times of something, right? So this one is moving up and down, and this one will go up or down, up or up, down. But whenever we select the two lines, so I don't know, I can do this. So if I select this row, then these two are meeting here, right? Oh, okay, I gotta select this one. There is another, this row and this row. They are meeting here. So if I apply 100 volts here, 0 volts here, and then when it is deflected, if I apply the voltage, then there is an electrostatic force. Electrostatic force, then there will be electrostatic latching. So in the next cycle, this guy is latched down, but the rest of them comes up. So which means, if you build this type of system, which uses hydraulic amplification, so that there comes the force, which can be amplified a lot, and then you can control it like a memory. So if you apply the voltage here and here, then at the intersection, it will be latched, right, because of the electrostatic force. So if we can build it, and then we can control the height, we can control these, we can build these piston arrays. Once we have the piston arrays, it's very easy to control these flows, right? So this is the research, and then it shows that we can actually we built this is the piston area, and then we built the channels on top, and then if we actuate the piston, we can close the flow. Maybe if we have 3 of these, 1, 2, 3 in sequence, maybe we can control its inflation one by one. Maybe we can generate the flows. So its force generated was over 50 million, which was very high and sufficient for this liquid control, so that we can replace all these fluidic connections. So now we know we can control air, and then we can control the liquid, and then we are moving towards the biological systems. So first of all, most 99% of the previous biological work was performed in the Petri dish. Do you know what is the Petri dish's problem? Is anyone taking medicines for allergy or anything? You will know that some particular medicine works for me very well, but the same type of medicine, but from another brand, doesn't work for me, right? It's a very common thing. Why is that? Because these type of testings have been performed only in the non-ideal environments. They do the testing in static environments. Static environments, cells grow without any flows. So there it does not experience any shear stress. As it doesn't experience any shear stress, its immunity or the mechanical structure won't grow into totally different. So whatever we do the test on that Petri dish, it might not be close, it might not mimic the real systems. So what people are trying to move toward is that they want to include the moving flows. So when cells, we can grow the cells under the flows, maybe it can represent the real systems better. Going back, this is exactly what we are trying to do. Now we know we can control the air circulation and liquid circulation. So we selected as the first step, we selected the brain, particularly the brain vessel, which is called the blood-brain barrier. The blood-brain barrier study so far has been done in medical schools in petri dish formation. It didn't go through much of the process. So the reason why we selected the blood-brain barrier is this. You can see this part, right? This part is white. The rest of them are stained. So this is the fetus of a mouse. And then when you dip the whole fetus into the stain ink, the rest of them are stained, but only this part remain white. That barrier is called the blood-brain barrier. Blood-brain barrier blocks 99% of all the drugs. When you have your grandmother or someone in your family have a Parkinson's disease, they take these drugs. It doesn't work. Why? Because near the brain, vessels are supposed to block 99% of all the drugs. It is so hard to control. It is so hard to predict. So this neurovascular study has been the major bottleneck of this drug development. Particularly, it can be evidenced by this drug success rate. If you compare it to cardiovascular drugs, this central nervous system drugs success rate is maybe a little more than 5%. So tens of billions of dollars are invested and only 5% succeeds. So that's the problem that we are trying to solve. So that we try to build this micro blood-brain barrier on the chip. Now, assuming we can control the flows, and then we can control both the air and gas flows. So current system, their testing is done in this way. So they grow cells. This is how medical schools have done this work. This is study for a long time. They grow the cells on top and bottom of these surfaces, or they produce these big hollow shapes, and they grow cells inside so that they can mimic the vessels. But as you can see, if there is a non-flow or very low flow, this barrier function basically tells us that there are very little barrier functionality. So, which means we tested these structures with the low flow rate, then the real system, the testing platform is not really representing the real system. So this is evidenced by the 4 vivid models in the past. These are all the works that previously we did. Most of them are static ones, there are recent dynamic ones. But the recent dynamic ones have very thick layers, so basically certain cells are not interacting with each other. So this is what we built. So this is the chip. We built the little channel. There comes the flow, and then there comes another flow. And then between them there is a little thin layer of the membrane where endothelial cell and astrocytes of the blood-brain barrier are formed. Once it is formed, we can fabricate it using the microfabrication techniques. And then we measured with three major aspects. First of all, cell frequency, and then electrical resistance across the membrane and permeability. So cells are growing well in the microchips. So these are the endothelial cells. Green colors show the nuclei, and they show very well. They are growing very well. And then astrocytes the same. And then even we can grow the neurons. And then we are integrating these sensors into the chip. So now we can have the electrodes made out of AgCl. And then we can measure the resistance across the membrane so that we can measure this permeability. So when there comes the drops, how many drops are crossing over, and then we can or how well these cells are formed, or these junctions are, how wide are they, so that we can measure those ones by measuring this resistance. So this is a tier measurement of results. So comparing This is a static measurement, which is done typically by the medical schools. This is what we measure. So the tear measurement, which is the resistance between these across the membrane, is much higher. These are the hundreds of resistance. These are the tens of resistance. So in reality, in real in vivo situations, the blood vessels show also hundreds of tear measurements. So microfluidic structures that we are building in vitro blood-brain barrier vessel model can actually model the real situation much better. Based on that, we can also do the testing for the permeability. So if we test the different sizes of these chemicals, coffee, you drink coffee. Why? Stay awake. Why does it work? Because caffeine has very low, very small particles. So this one is a Stokes radius. Stokes radius means basically the diameter of your molecules. If you drink caffeine, it just goes through the blood-brain barrier because it's small. But if you move up toward on this side, like an interval, then suddenly it doesn't work. But this is the area that most of the drugs are. So the in vitro model that we built is based almost exactly mimic these systems, and then this is the in vivo system. So we believe that this structure is very feasible and valid alternative to study this blood-brain barrier. So this is the summary of the structure. So we built these two fluidics, row cell culture between these two. This area is where the cells are grown, endothelial layers and the astrocytes. And then if we put some drugs that are supposed to widen these junctions between this cell and this cell, there is a junction. That junction sometimes opens up under certain chemicals. So one of the chemicals is histamine. We apply the histamine, and then suddenly the electrical resistance across this membrane dropped, which means this tight junction has opened up and let these chemicals drugs go through temporarily, about 5 minutes. So we have this micro-BBB model could enable the observation of co-culture here and permeability characteristics. So to test the different kind of shear stress or conditions, we made the channels in different formations, different width, and which will result in different velocity. Different velocity will cause the different shear stress. Different shear stress will affect the cell growth very differently, and then different cell growth will tell us that which drugs we can come across the membrane and under what conditions they're done. So these are the summaries. So let me conclude the talk. So far we have developed a unique pumping technology for compressible gases using continuous induced pumping, and also we developed a high force actuator for pneumatic release liquid pumping using hydraulic amplification. And then we mimicked cerebrovascular environments in the integrated platform. We saw tight junction expression. We built the dynamic environment with the shear stress, and we measured the tear management and permeability. And then the measurement results of this BBB blood-brain barrier platform integrating all of this showed the very high promises that it can be used to monitor changes in barrier function of various stimuli, and also predict the delivery of drugs across the BBB. And then we plan to continuously expand our research for the other body parts to go back to the original vision of this organs of the chip. So these are my students, PhD students, particularly last group, bioengineering and Moses Snow are mostly work on this project. And then Jung is working on these fluidics parts, and my other group members are working on other projects. And then we have also visiting professors and undergraduate students who I very much feel grateful for their efforts. So if you have any questions, I would like to answer. Thank you very much.
On your pendulum experiment, did you calculate or have the guys calculate what the resonance of that pendulum would be? And are you just driving it at its resonance to make it so displacement so large?
Yeah, you missed the one thing. So pendulum resonance is determined by the distance of the thread. Right? So it, right, exactly. So if you have the longer one, then it will get slower. So resonant frequency is actually determined by the length of the thread, and then we just modulated this signal on and off with that frequency. So the membrane resonant frequency is 70 kilohertz. But we can, like electrical engineer, like amplitude modulation. Right? We do this. We are sending the signals. This is a 70 kilohertz. We can modulate the signals like this. And then this could match to the resonant frequency, whatever it is, of this thread. So that this resonant frequency, this was a 70 kilohertz. This one was actually I don't remember. We can see the previous one. Yes. Yes.
On the blood-brain barrier model that you created, you employed your own micro pump to do that, right?
Yeah, for testing we did some of the tests we did. It's actually at this moment it's not a critical factor because the critical factor is that whether this BBB model really mimics the system. The micro pump will play the role when we want to build the closed loop system.
Right. So have you developed a closed loop system?
We have separated the systems. We can connect them, but we never did. I mean, we did, but we don't need to do it. Any other questions? Okay, then I will